Hello, everyone. Today we're going to start our discussion on Chapter 9, which is hypothesis testing. Now, hypothesis testing, this is a little different than the hypothesis testing that you might have learned about in science class. Basically, what we're going to do is we're going to have two different alternatives. We're going to look at a null and an alternative hypothesis, and we're going to try to prove if our alternative hypothesis is true. So let's start with a few definitions. So here is our null hypothesis. So the null hypothesis is what we're going to revert to if the alternative cannot be proven. So essentially, this is also what we begin the test assuming. So we're going to assume that this null hypothesis is true. It's usually set as an equation, and we use the symbol, we call this H naught, to represent this null hypothesis. Now the alternative hypothesis, this is what we're going to be considered and proven. Okay, so the burden of proof is on our alternative hypothesis. So what's going to happen is we're going to see something like, do the data indicate sufficient do the data indicate sufficient evidence to conclude? And then what'll be here is our alternative hypothesis. So basically, we have to have the evidence in order to do this. It's usually going to be a not equal to, a less than, or a greater than. And we use the symbol HA to represent, oops, typo right there, alternative hypothesis. So then we're going to be doing a hypothesis test. This is going to decide whether the null hypothesis should be rejected in favor of the alternative or not rejected. And notice I say rejected or not rejected. I use that almost kind of a double negative in there instead of saying accepted. So one thing we want to be very careful not to do is accept our null hypothesis. We simply just fail to reject it. And then we're going to have a significance level. So this is the probability. So we're going back to probability now, why we had to learn that. The probability of making a type 1 error. That is the probability of rejecting a null hypothesis when it was true. And we're going to use that as a Greek letter alpha. So the alpha is our significance level. Okay, so basically, we don't want to reject a null hypothesis when it is true, because then we're saying we have enough evidence to show something where we had enough evidence, but apparently we were wrong, or evidence was incorrect. And usually that happens because of, well, simple randomness, because remember, we're going to be taking samples in order to perform these tests. So let's take a look about what hypothesis tests and criminal justice system. Now we have our null hypothesis, which kind of looks like this, and this mu naught, that's going to be a number that is given in the problem usually. So we have this null hypothesis that mu equals some number. Okay, we can call that number 10 or something. So let's say I have an original hypothesis that mu equals 10. That means the accused is not guilty. Okay, this is what we assume until we're proven it is guilty. So we have our alternative hypothesis. This goes as HA. This means mu, in this case, let's just do not equal to 10. Nope, mu is not equal to 10. Mu is different from 10. And that means they're guilty. Okay? They're guilty of the mu is guilty of being different from 10. And this is what we have to prove. We do our test in order to prove this. And you'll see how we're going to do that test in just a little bit here. So we perform our test, and we have two different outcomes on our test. We can either reject the null hypothesis, and that's when we define the defendant guilty. if we reject the null hypothesis, we say the defendant is guilty of being different from 10. Okay? Or the other possibility is do not reject. This is said not guilty, because if you think about in the court of law, when they stand up in the court of law, they don't say the defendant is innocent. They say the defendant is not guilty because they didn't have enough evidence to convict them. So if we don't have enough evidence to convict, so here the mean is not statistically different from the proposed mean. That doesn't mean that it is. And this doesn't mean that somebody is innocent. It's just not statistically significantly different. Here we didn't have without a reasonable doubt. Here we have statistical significance. So our significance level alpha, this is the probability of rejecting the null if in fact it were true. Okay, this is convicting an innocent person. This is something we want to avoid. So we try to make sure and control this number at this alpha level. So we know exactly how sure we are that we're not doing this and we're not convicting the innocent person. Now, what we consider a type 2 error, that's the probability of not rejecting the null hypothesis when in fact it's false. So that's like we didn't reject it. We didn't have enough evidence to say that mu was significantly different than 10, but it really is different than 10. We just can't prove it statistically. That's the chance of letting the guilty person walk. Okay, we didn't have enough evidence, so we kind of just threw up our hands and went, okay, well, probably guilty, but they have to walk anyway. So in this case, we go, well, it's probably not 10, but I can't prove that it's not 10, so I have to go on with my life. Maybe I need a bigger sample size, something like that. Okay, so here's how we can set up a hypothesis test. So the first step in setting up your hypothesis test is write your null and alternative. So this is what you're going to do first. And I really emphasize this, even before you're going to get to use your calculators, but even before you go to your calculator, the first thing you should be doing is writing this down. Your ho and your ha, okay? And we'll see the same example we had last time. And then we're going to find what we call a test statistic. So that's a Z or a T value. And then we're going to find something we call a P value. Okay, this is going to tell us, this is the information that we need to make our decision. This is the proof that we're looking for. So we find either this or this, our Z or our T. We find our P value. And then we're going to make a decision and a conclusion. Now, every single time that you do a hypothesis test in this class, I need every piece of this. Not writing down every piece of this, you will not get the answer correct. Even if you just say no or yes or something like that, that's not the correct answer. The correct answer is H naught, HA, your test statistic, your p-value. Then you're going to tell me whether you reject or do not reject. Then you're going to tell me if you do or do not have enough evidence to conclude the alternative. So this is everything you have to do. So I'm going to write this down. You must have all 5 parts of a hypothesis test. So every time I ask you to do a hypothesis test, I'm asking for these 5 things. Most of your hypothesis tests in your homeworks are worth at least 5 points. On the tests, they're usually worth 10 because it's usually 2 points per step. Okay. How do we choose an alternative hypothesis? Well, the way that we can do this is the main question we're asking goes in the alternative. So do the data show enough evidence to say a drug increases sleep on average? So this might be, so if it increases sleep, then we're saying that the mu is greater than 0. So we're saying that there's more sleep with the drug than without. And the alternative, or the null, always equal. So our alternative is either going to be less than, not equal to, or greater than. In this case, it's greater than. If it's greater than, it's considered a right-tailed test because we're only concerned with whether it increases sleep. That's what we're trying to prove. So we're trying to prove whether this increases sleep right here. Is the average number of robberies in major American cities different from last year's mean of 94? So is it different? Do we have enough evidence to conclude that the average number of robberies in major American cities is different from last year's mean of 94? So different from. This is called a two-tailed test. And this would be a not equal to. So different from goes here. This is considered a two-tailed test. Does regular exercise lower average systolic blood pressure to less than 120? So we get a sample, right? Get a sample of people. We have them do regular exercise. We monitor that, and we take their blood pressure, right? We see if that blood pressure is lower than 120, that systolic blood pressure. And that is less than, so that is a left-tailed test. So we see the less than, we see the word increase, we see the word different from, we see the word less than. But basically, that's what you're looking for. That's why the first thing I like you guys to do before you do anything is write down your null and alternative. So let's talk about errors a little bit. So I talked about this before when we were looking at the comparison to a criminal justice system. But in this case, I just want to show you something. So we have our H naught and our HA, and I'm just going to use 10 again because it's an easy example. Okay, so we get our test statistic, we get our p-value, we make our decision. I can spell decision, I really can. There we go, I just had a moment. Okay, we get our decision, and then I want to look at this. Now, if I failed to reject the null, so I didn't reject the null, wasn't able to, I say, well, no, mu could be 10. And then we find out, no, there is no difference. Mu is about 10. So this was the correct decision in this case. But if I didn't reject it, so I said, do not reject null. We do not have enough evidence to conclude that mu is not equal to 10, and that is false. So I did not reject the null, but the null isn't true. It's not equal to 10. It's something else. It's 11, it's 9, it's something else. Okay, so if I did not reject it, so I kept it, kind of, okay, I said, well, mu could be 10, and mu is not 10, then I committed a type 2 error. Now, we do not control this. And if we don't control it, that means that we're saying that the mu could be 10. That's why I never conclude the null hypothesis. I never say, well, I accept it. Mu is 10. Okay, mu is not 10 necessarily. It could be. We can't prove that it isn't. You see the difference? It's very minute, and it's a little bit weird, but it was not saying that that guilty person is innocent. We're saying that we don't have enough evidence to say that they are, because we can't control that type of error. So then if we reject the null hypothesis, so we rejected the null in favor of the alternative. So we said we have enough evidence to say mu is different than 10. Oh, we find out later that mu was 10. Uh-oh. So we go, oh no, that's not good, because we now have committed a type 1 error. This is the one we control, and we keep under either 1%, 5%, or 10% usually. We want to control this, and depending on what we want to keep this under. We want to keep that underneath 1%, 5%, or 10%. If we do reject the null, and then the null is false, well, good. We've made the right decision, right? If we say mu is absolutely not equal to 10, well, it's not, so that's fine. So we're good with that. So we will do a demonstration in class. I think that's going to also help a little bit with this. and understanding these things, but generally speaking, a type 1 error is considered alpha. A type 2 error is considered your beta. And this is probability of type 1 error is alpha. Your probability of type 2 error is beta. We don't control this one, so there's not much we can do about that. Okay, so let's talk about that test statistic and p-value that I've been putting off. So a test statistic is just the standardization of the statistic that we have. So it's the standardization of, in this case, X bar, if the null hypothesis were true. So if the null hypothesis is true, then X bar is going to have a normal distribution with the mean of mu naught, whatever our hypothesized mean is. So for our other example, when we guessed that mu naught was 10, so then X bar, if the null hypothesis is true, X bar will follow a normal distribution, if of course the central limit theorem holds, right? With mean of 10, and the standard deviation with mean of 10 and standard deviation sigma over the square root of n. So I'm going to need these pieces of information. So you notice I say sigma. This means I need the population standard deviation. It's not the most realistic thing ever, but it sometimes can happen. So what will happen is, for a sample mean where sigma is known, of course, this is how we would standardize it, right? X minus mu over sigma. So X bar minus mu naught over sigma over the square root of n. So then we see what the probability is that the test statistic is at least as far from 0 as it is. This is called the p-value. So if I put a shot in the dark and I said, well, my X bar I got was right here. I went and got an X bar that was here. Or actually, let's do this example that I've done over here. So I went and got an X bar. It looks like it's way over here. So I got an X bar that's way over here. So then what happened is when I standardize that, I get my standardization is negative 2.65, which is way, way over here, okay? That's pretty far away from 0. This is the standardization, so this is Z. So that's pretty far away. That's pretty unlikely that if the null hypothesis were actually 10, that I'm going to go out here and get something that small is extremely unlikely. So that's what's happening here. So in a two-tailed test, we'd actually have to look at both sides. So in this one, in this particular, we're looking at mu is less than 10. So we're actually just looking at a what we call a left-tailed test. And now you can see the left tail is the p-value. So we look at how far this is away, and what is this probability right here? That is our p-value, okay? That is the probability that our test statistic is at least as far from 0 as it is. So it's either this far from 0 or actually farther, and that's called our p-value. So how unlikely is it that I go out and get a number that's way over here below 10 if 10 were actually mu? Well, highly unlikely. That's like 2.5 standard deviations below the mean. That would be extremely unlikely. So I would say, well, if that's so unlikely, then chances are this is not 10. So I would reject the fact that that was 10. And I would say, that's not 10. Can't be 10. Well, I guess it could be. It could be with whatever this probability is. But that's such a small probability that I'm able to say, well, I reject that. And that's essentially what we're going to be doing with hypothesis test. So here's a little more about what p-values look like. So if I have a two-tailed test, this is where the null hypothesis is mu is not equal to some number mu naught. This is my left-tailed, mu is less than some mu naught, and this is my right-tailed, mu is greater than mu naught. So you can see what these p-values look like. So here, when it's not equal to, I actually have to take my Z that I found, my standardization, and then I find this area but then I have to multiply it by 2, or I have to find this whole area somehow. There's a couple different ways to do it that we'll talk about in a little bit. And then mu less than mu naught, well, this time I only need, of course, the left tail. So 2 tails, the left tail, and the right tail. And these are my p-values. This area is my p-values. Okay. So here's another way to think about p-value, because I really want you guys to understand this. This is probably one of the most important things to take from this class, is to understand what a p-value is. So here we have our probability density function. You get that idea. And of course, out here, like we said, very unlikely observations. Here, these are the most likely observations. And out here, we're going to have very unlikely observations. And we have a data point that's right here. Okay, so we went out, we got an X bar, that X bar landed right there. Remember, this is our probability density function if the null is true. So you see, we assume that it is true and try to prove that it is not. So this shaded green area, that's the probability of an observed or more extreme, okay, result, assuming that the null hypothesis is true. Now this looks like a right-tailed test. So the vertical coordinate, of course, is our probability density computed under the null hypothesis. The p-value is the area under the curve past the observed data point. So you can see how, if this gets farther away from the mean in the middle, as this gets farther away, what happens to p-value? It gets smaller as our observed point gets farther from the center. Okay, so we can see that as this gets farther away, this gets smaller and smaller, because our chances of this being the observed data point, if this is actually true, get tiny. It's ridiculous to even think about anymore. So here's how we can find the p-value for some z-tests where the population standard deviation is known. So let's say that we are given, in this case, we are given our test statistic, and we need to find our p-value. So it really is just using normal CDF. That's all it is. So for a two-tailed test, there's actually 2 ways to do it. I actually prefer this way myself. So let's say that I had a test statistic and I were testing mu is not equal to 10 again. Okay. So I was testing mu is not equal to 10, and I got a test statistic of, let's do the one we were doing, negative 2.65. Let's do that one that we had before. So what I would do is I would actually want to find the area, negative 2.65, 2.65. So I want this area right here, but I also have to consider this area. Because remember, all I want to know is what's the probability it's as far from 0, which means it can be on either side. This is actually z now, because this is, once I do have the test statistic, I have it standardized. And yes, you do have to report the test statistic. So I go to my calculator, and I'm going to go, so I want 1, because this whole thing is 1, minus the area between here. So I want 1 minus, and then I remember I go distributions, normal CDF. I'm going to go from the negative 2.65 to positive 2.65. My mean, I still have 0, 1, because I'm doing this, I'm using z's, it's already standardized, and I say enter. Enter. And the p-value here is 0.008. Okay, so let's look at this one. This one, I only want the left tail, so I only want this one. So in that case, I'm going to go distributions, normal CDF. Now I'm just going to go from -10 up to -2.65. So if this were, remember this is if the null or the alternative hypothesis is mu is less than 10. And then, or mu is less than any number, I should say. Let's just say 4. You can say 4. It doesn't matter what it is. This, and remember, this is just a negative infinity. You can say -99, -265. I don't care. So my p-value for this one is 0.004. And then for a right-tailed test, I'm going to go normal CDF from 2.65 up to some positive infinity, 587. It doesn't matter what it is. I made it up. And that is the same p-value because we had the same number. So here our p-value is 0.004. So this would be if mu was greater than some number 26. It doesn't even matter what the number is. What really matters is our test statistic. And then here we assumed our test statistic was -2.65. Here we assumed it was positive 2.65. So we're going to be doing a lot more examples of these in class also. Okay, so let's talk about interpreting. Okay, you can laugh now. Interpreting the p-value. The guidelines for using the p-value to assess the evidence against the null hypothesis. So very tiny p-values, because let's just use the example right now of a right-tailed test. So over here, I have a teeny tiny p-value, right? I have a really tiny p-value, which means that this number is really far away from the middle. So that means I have very strong evidence against the null, right? So this means that the null is probably not correct because this is so unlikely. Because if this p-value is less than 1%, that means that had a less than 1% chance of happening. If it's between 1 and 5%, I consider that strong evidence still. Okay, it's a little bit farther over. So still pretty small. Still not very likely. It's considered statistically significant. Very strong is considered highly significant. Okay, move it over a little more. Okay, now it's between 5 and 10. If that's going to be where I get it, then I'm looking at moderate. So I'm tending towards significance. Sometimes people will accept these, I shouldn't say accept. Sometimes people will use 10% as their significance level. Sometimes in psychology they do that because it's really hard to prove anything in psychology because people are so variable. And then if it is greater than 10%, so if your X bar is over here, that's a big p-value, look at that. So if your X bar is over here, that means that here's your mu, here's where you tossed your net. Well, of course it could be because it's so close. That is definitely something that could happen. So if you have a high p-value, if you get a p-value of like 30%, you're like, well, sure, something that can happen 30% of the time happens sometimes. So when our p-value is really high, close to 0.5 for a one-tailed test or close to 1 for a two-tailed test, we know that these two values are very close together, and therefore we have weak or none. We're not statistically significant. So we absolutely cannot reject that null hypothesis. We don't have enough evidence. It's too close. The value that we got and the value of the mu are too close together. Now, there could be a lot of reasons for that. It could be too small of a sample size. We weren't able to get far enough away by the sample size. Because remember, this particular curve is made up of, remember we have x bar minus mu naught over sigma over the square root of n. So you can see the larger that n is going to get, if we get a larger n, this is going to get closer together, and thus if we get a certain point right here, that certain point might be somewhere else, even if it is the exact same number, because our standard deviation will be smaller. Okay, so how to perform the test and make our decision and conclusion. So the first thing we want to do is we take the p-value that we had and we compare that to the given significance alpha. Or if none is given, if no alpha is given, we just assume it's 5%. If the p-value is less than or equal to our significance level, then we reject the null. So small p-values get rejected nulls. Okay. If it is greater than alpha, then we have too high of a p-value, then we cannot reject. So large p-values cannot reject. And our conclusion looks like this. If we do reject, we say something at the 100 alpha percent. So if this alpha is 0.05, we would say at the 5% significance level, we have sufficient evidence to conclude that, now we restate the alternative hypothesis in words. I prefer it in words. If you don't have words, so we might say mu is not equal to 10 if we don't have any words. Or we can say the mean blood pressure is not less than, or is, we have sufficient evidence this is, or the mean blood pressure is less than 120, something like that. So I prefer to go back to the original question and answer that question. If we do not reject at the 5% significance level, we do not have sufficient evidence to conclude that, say, the crime rate is different from last year's of 94. I don't think it was crime rate. I think that was the number of crimes or whatever, the mean number of crimes. I forget what it was. Is different from last year's of 94. Mean monthly crimes. I don't remember what that was. Okay, so I have a couple of memes to help you kind of remember these things. So here's some memes. So you can pick which one you like the best. I'll show these to you guys in class too. So, hey girl, you must be p greater than 0.05 because I failed to reject you. Because we don't reject things that are greater than 0.05. And the most interesting man in the world says, I don't always reject the null hypothesis, but when I do, it's because I found a small p-value. And the best one ever is this one. Snoop Dogg. Snoop Dogg says, if the P is low, then the hoe must go. I have to say no more than that, except for that hoes are garden instruments. So, and then I will sign off for this one, and we'll start on 9.2.